Suppose a polynomial f of x is divided by x minus c and yields the relationship f of x equals q of x times x minus c. Again, that's our quotient times our dividend plus r. Then the remainder, r, is equal to the value of f of c, or in other words, f of c equals r. Okay, so fancy speak for saying that when we do synthetic division, that's the same as evaluating the function at a particular number. Okay. Now, in general, so we have this f of x equals x minus c times q of r plus r. If we were to evaluate it at f of c, kind of think about what happens algebraically, we would get x, we're going to replace x with c, so c minus c times q of x plus r. What happens to the c minus c? Right, that part goes to 0. And so we're really left with r. Just a real quick, oh, that's why it works that way. Okay. Now, that said and done, now sort of got the old way and the new way. The old way of evaluating functions is to type it in and work it out term by term. The new way is to use synthetic division. So finding the remainder of when c is 5 given this function, that's in other words just do synthetic division. So make a list of my coefficients. -1, 11, 7, and -19. And I'm going to synthetically divide in. Now, it's not in, notice the form the number's in. Saying c is 5 means we're going to evaluate it, we're going to find f of 5, right? So f of 5 does not mean to switch the sign. That only happens if we're staring at the factored form of the number. We're staring at the function form of the number. So I'm just going to synthetically divide that at 5. Drop the -1 down. Multiply, combine like terms, multiply, combine like terms. 150 plus 30, so 185. And we get 166. Okay, so the whole moral of the story here is f of 5 equals 166. Hopefully you feel like that's a little bit quicker than having to work it out by hand. Same thing with next door, we got a different function. So make a list of my coefficients. It's a constant. Maybe I should write down the coefficients. So the coefficient of x cubed is 1, then 4, -7, and I don't have a constant, so I put a 0 in there. And evaluate that at 5. And so we drop the 1, multiply, combine like terms, multiply, combine like terms, oops, that's 45, isn't it? Oh, good thing I caught that. Combine like terms, we should get 38, and then 5 times 38, let's see, 5 times 30 is 158, another 40, so it's 190. So we get 190 there. Okay, so f of 5 happens to be 190. A complex number, c, is said to be a 0 of a polynomial if f of c equals 0. So if we substitute c in for x in the function and obtain a 0, then we have a 0, or a root, or a solution of the function. Okay, so let me just take a second and sort of map out an idea of this. So let's say we've got some polynomial, p of x equals, and I'm going to make up some very generic coefficient of x to the n plus some other coefficient x to the n minus 1 plus some other coefficient. Now, don't worry about the the terminology here plus dot, dot, dot. Okay, so I'm basically saying I've got a polynomial that has coefficients and variables, 3x to the fourth plus 7x cubed minus 4x squared minus something, right? If I know that P of C is 0, then I know a couple of things. So if I have a number that when I evaluate it in that function I get a 0, I know that C, the number C, is considered to be a root of the function. I also know that x minus c is a factor of the function. I also know that let's try this again. X equals c is a solution of the function. And that c itself is a 0 of the function. Okay? So all of these words, root, factor, solution, 0, they all mean the same thing. And what do they mean? They mean where does it cross the x-axis? They're all very fancy words for saying x-intercept. They all have their different forms. X minus c is the factored form of the x-intercept, whereas x equals c is the solution form of the x-intercept. But we're all talking about the exact same idea, that they're interchangeable information with each other. Okay, knowing that these terms are interchangeable, that allows us to ask some different questions now. So we're going to give a polynomial, and I'm going to ask, is a number a 0 of that polynomial? All right, so what I'm asking is f of, in this case, -2, right now I'm not sure, is that equal to 0? Okay, so to find that, I'm going to use synthetic division. So make a list of all of my coefficients. So 3, 2, -1, and 6, and evaluate it at that number at -2. So drop the 3, multiply, combine like terms, multiply, combine like terms, and combine like terms is the last one there, and that gives us -8. So -2 is not a 0 of this function. We'll try this other function then and see if -2 is a 0 of it. So x cubed, x squared, x in constant, 1, 2, -4, and -8. Evaluate that at -2. So we'll drop the 1, multiply, combine like terms, multiply, combine like terms, and we do get 0. So -2 is a 0 of this particular function. All right, so let's take something like x squared minus 9 equals 0. Let's just go through a previous set of skills and apply what we've known, and then just throw some vocab from this section attached to it. So x squared minus 9 equals 0 is an example of difference of two squares. So I would factor it, and I would get x minus 3 and x plus 3 equals 0. And then I would solve. So that would be x minus 3 equals 0 and x plus 3 equals 0. In which case, I get x equals 3 and -3. Right? Now, let's kind of remind ourselves some things. So when we factored x minus 3 and x plus 3, that means x, trying to write that a little bit nicer, x minus 3 and x plus 3 are factors of this polynomial, whereas 3 and -3 are solutions or roots of this polynomial. In other words, it's different clothing, but it's the same idea between the expression and the number form. Okay? So the factor theorem is, let f of x be a polynomial and c be some sort of complex number. Then x minus c is a factor if and only if f of c happens to equal 0. Okay, so in other words, what that means is if I do synthetic division and a 0 shows up, then I know that expression of x minus c has to be a factor of the original polynomial. So if c is a 0 of the polynomial, then x minus c is a factor of the polynomial. In other words, the solution form, the 0 form, is connected to the factored form. Okay. All right, so we're going to be given a third degree polynomial, like a nice cubic here, and we're going to be told to divide by x minus 2 and find the resultant zeros. So the hope is that x minus 2 is a factor of this. So we're going to go confirm that. So set up synthetic division, x cubed, x squared, x and constant. So 5, negative 39, 52, 12. And the factored form is x minus 2, so what are we going to synthetically divide by? That means we're going to synthetically divide by positive 2. So we got to switch the sign. Okay? So if the factor is x minus 2, then the 0, the thing that we're testing to see if it goes into it evenly, is actually 2 itself. Okay. So let's do the process. So drop the 5, multiply, combine like terms, multiply, combine like terms, multiply, and we in fact do get 0. Okay, so all of that means f of 2 happens to be 0, so 2 is in fact a 0 of the polynomial. Okay, so our factored form then is, we have x minus 2, and then that's where we're going to collect up all of our coefficients. So that 5 underneath the 5 really means 5x squared minus 29x minus 6. And then, now that it's quadratic, we can go back to our lovely quadratic skills from previous lessons. So it is factorable. And if it's been a while, I suggest you pause the video and then see if you can figure out the factors. This would be 5x and x. And let's see, so if I get the 5 and the 6 to multiply, that'll give me a 30 and then 1. And I want that to be negative and that to be positive. So our factored form is x minus 2 times 5x plus 1 times x minus 6. Which means, equivalency, the zeros of the polynomial are going to be 2, negative a fifth, and positive 6. Take each of those, set it equal to 0 and solve. We should end up generating all those numbers.